Our discussion today is going to focus on loop traverses. First of all, the traverse we're looking at for these type of computations is considered a closed loop. That is, it starts and ends in the same place. Generally, in the field, it's best if we measure these in a counterclockwise direction, which allows us to measure interior angles directly. That is, we measure angles to the right, as is typical, and when we do this, moving counterclockwise around the loop, then we're going to be measuring interior angles directly. We're also assuming that angular closure is within the acceptable limits, and we'll refer to acceptable limits here in a little while. And then we're going to need to have some starting azimuth known or assumed. Sometimes we may assume something and adjust it to something known later. We'll also need a starting coordinate to be known or assumed. Okay, what I have for you here on page 41 of your orange book is an example problem that is really pretty based in reality. And let me help you understand the scenario that makes this necessary. In this little scenario that you can see at the bottom of this page, what I have here appears to be some kind of tract of land on which we have a house, perhaps a machine shed, and along the west side we have a township road. At the southwest corner of the tract there is the intersection of a township road, and that road runs, maybe a quarter mile or so, maybe less, to the east and dead ends in what appears to be some brush or some trees. And in this case, you've been hired to do a simple boundary survey. The owner has a pretty good feel for where the property corners are, and there is a fence that seems to follow two sides. And your task is to verify that, yes, those are indeed the property corners, if they are, and then come up with lengths and directions of the sides. After some field reconnaissance, you have discovered that indeed there is a corner that is marked with, say, a buried iron pipe down here at what we call the southwest corner of the southeast quarter of section 18, Township 18 North, Range 10 East. Then a half a mile or a quarter mile east along that line, you have found another point marked as the southeast corner of the southwest quarter of the southeast quarter of that same section. Then you followed the fence line to the north and found at what we're showing as point 3 here, another iron pipe buried in the ground. And it's not too far from the fence corner that you found here at point 4. And then over here by the West Township Road, you found the end of the fence, and then nearby you found another iron pipe buried in the ground. And it appears that all 4 of these have been set at approximately the same time. You have a strong reason to believe that these are original corners of this boundary. In an ideal world, if everything was billiard table flat and no trees grew anywhere, then you could set up an instrument at Q, and you could measure directly to point 1, and maybe even turn the angle over here to point 5. And if all was well, you might even be able to see clearly over to point 3. And it would be a simple exercise in direct measurement and trigonometry, and you could come up with the length of all 4 sides. However, rarely does reality cooperate with us in that way, and we have to work around things like terrain and vegetation and structures, man-made objects of all sorts. Sometimes I've had to traverse around corn because it was too tall to see over. However, if I had been there 6 months earlier or 6 months later, then I'd have no problem at all, and I could simply shoot directly across the field. But traversing allows us to work around obstacles. I'd like you to consider here that you've got some stands of trees here that are in the way. You can't see directly from Q to 1. And likewise, you can't see directly from 1 to 3. Nor can you see 3 to 5 or 5 to Q. I've given you an obstacle on every side. In the field, the survey crew chief is tasked with devising the best way to find the relative position of these points. In order to do so, he could simply measure the lines QP, PN, NM, and ML and get those relative positions, and then relative to those points, measure angles and distances to points 1, 2, 3, 4, 5, and 6. However, as you have learned, we're all about error management. We need to ensure that we haven't made some kind of blunder. So therefore, we prefer to make loop traverses. That is, a loop of lines that close upon themselves, giving you some kind of irregular polygon. We know that in this case, if we have a 5-sided polygon, then the sum of the interior angles of this 5-sided polygon will be 540 degrees. Well, if we measure every side of this polygon and measure every interior angle, we will be able to determine how closely we have adhered to this 540 degree theoretical sum. We know there will be a difference because we know there is an error in every measurement. However, if we are minimizing those errors, the sum of our errors should still allow us to get pretty close to, reasonably close to, the theoretical sum of the interior angles. So in the process of putting the instrument in positions with which we can make measurements to points between which we must actually, in this case, indirectly measure, then we also have to put these instrument points in locations where the basic instrument points are intervisible. That is, if I have an instrument sitting at P, I need to be able to see Q and N. Where's N going to be? Well, it's going to be where the party chief puts it in order to ensure visibility to M and P. Likewise, M is chosen, just like any of these except Q. M, N, P, and L are all chosen by the survey crew chief. Locations selected to maximize visibility not only to the boundary and other feature points that we want to measure, but to other points on this traverse loop. We measure these lines of the loop, and let's speak primarily about the 5 sides of this irregular polygon. At these vertices that you see listed here, these are the angles we measured. And then these are the lengths of the lines that were measured. Well, in our case, we can either assume a direction or perhaps we already knew a direction of a particular line, and we either knew or assumed a northing, that is a y value, and an easting, an x value, for some starting position. Whenever I see 5,000, 5,000, that's a clue to me that that's very likely an assumed position. Well, you know that the interior angles that are measured there at these 5 vertices are all going to contain error. I can find that error by summing those interior angles. I know if I have 5 interior angles, the theoretical sum should be 540 degrees. But in this case, I've found that indeed I have 539 degrees, 59 minutes, and 40 seconds, which leaves me 20 seconds short of the true theoretical value. I really don't know where those errors are, and I don't know the size of each error. All I know is the sum of those errors. A few of those errors may be negative, a few may be positive. They may have a net canceling effect, but the sum of all those errors, in this case, is a negative 0 degrees, 0 minutes, and 20 seconds. What I must do is adjust all my interior angles. I simply take my error, which is a negative 20 seconds, and I generate a positive correction. In this case, it's a positive 20 degrees divided by the 5 angles that I measured in the field, giving me a 4-second per angle, a positive 4-second per angle adjustment. Well, if I apply that to each one, 75:01:24 plus 4 seconds gives me 75:01:28. And so forth on down the line. And you'll see that here, once I resum my adjusted angles, they come out to 540 degrees. Now, this doesn't make those angles perfect. It just makes their sum hit theoretical perfection. But there is still some error in those angles. And we will see the effects of that as we go with our computations. We need to generate azimuths for each side of that loop. We have a simple rule that you can see listed here on the bottom of page 42. Two rules, one for counterclockwise computations and the other rule for clockwise computations. This is an example of the azimuth computations. We started with 76:32:44 for the azimuth of QP, and as we progress in the counterclockwise fashion around this loop, you can see us applying the interior angle at each vertex to the back azimuth of the previous course. And eventually, I get down to the end, and I need to check myself. You see, the last remaining unknown azimuth in this case occurred for line LQ. Well, I'm not done because I really need to prove to myself that I've computed this properly. So, once I find the back azimuth of LQ, then I can apply the last interior angle, and this should give me the azimuth of my starting line. If it doesn't, then I know I've made a math error somewhere and I need to find it.